Hello, in this video I want to talk about how to integrate absolute value functions and also how to graph absolute value functions. We are supposed to be able to graph them at this point in time. So that should be a review, but if you never really picked it up, then this is your chance to learn how to graph absolute value functions. And the graphs of the absolute value functions are the ones that are going to enable us to find the integral by thinking about the area of the functions. So here's an example: the integral from 0 to 6 of the absolute value of 10 minus 2x dx, and I think it's very similar to the one example we were working in class when the bell rang. So I'll try to take the integral of this, but before I do that, I want to talk about the most basic of the absolute value functions, which is the absolute value of x. And most people know what the graph looks like, and many people say it's got a V shape, and that's true. So there's the graph of the absolute value of x, and you would find points like 1, negative 1, 1, 2, 2, 3, 3, and then on the negative axis you would find negative 1, negative 1, negative 1, 1, negative 2, 2, negative 3, 3, and that's the graph of it. But what I want to concentrate on is that the absolute value of x is actually a piecewise function. And so I can write it as a piecewise function, and the two pieces are positive x and negative x. In pre-calculus, if you recall last year, we went over the fact that the absolute value of x is the same as plus or minus x. And so, because it's a piecewise function, now you have to give a domain for each piece of the graph. And so we would say, when is the function equal to the positive x? Well, it's this side over here. This is y equals positive x. And this other side is y equals negative x. So then when you assign a domain, you say the absolute value of x is equal to the positive x when x is greater than 0. And the absolute value of x is equal to the negative x when the x is less than 0. And if you want to, you can include 0 on one of them, either the top or the bottom, it doesn't matter. Some people include it on both. I would just include it on one. So maybe there. And that would be a piecewise representation for the absolute value of x. Well, what about having something a little more complicated, like y equals the absolute value of x minus 2? Then how would we break this into a piecewise function? Well, all you have to do is say that one piece is going to be the positive x minus 2, and the other piece is going to be the negative x minus 2. And then you have to figure out a domain for each one. So there's your classic plus or minus idea. How do I figure out the domains? On the first example, it was just from the graph you could figure out that when x is positive you see that piece, when x is negative you see the other piece. Here, if I don't have a picture of absolute value of x minus 2, then it's a little harder to think of the domains for those two pieces. But here's one thing you can do. We take the argument of the absolute value, we take x minus 2, and we set it equal to 0. And so that says that x is equal to 2. And so x equal to 2 is going to be the point of interest. And something happens to the right of 2 and something else happens to the left of 2. So now I'm going to create a little number line, and the point of interest 2 will show up on the x number line, and I test values to the left and to the right. So for instance, if I were to try a number to the left of 2 like 1, and I plug it in to the argument, not to the entire absolute value, but just to x minus 2, the argument of the absolute value, then I will get 1 minus 2, and that would be negative. And if I try a number to the right of 2, like 3, and I plug it into the argument, then I'll have 3 minus 2, which is a positive 1. And so now I know what the domain pieces are for the piecewise function. So think about what gave you the negative and which piece gave you the positive. The negative came to the left of 2. So then see this negative right there? That came by letting x be a number to the left of 2. So then the domain for this piece would be when x is less than 2. And the positive came from letting x be a number to the right of 2, which was 3. So then this was the positive here, the top function. So that was true when x was greater than 2. And again, you would assign one of them to be equal to 2, doesn't matter which one. Sometimes you'll see that people assign it to both. Just choose one. And this will guarantee that if you don't use the absolute value, you still get the right number. For instance, choose a number that's greater than 2 and plug it in here. Let's say 5. 5 minus 2, that would be 3. And so now try the 5 in the original absolute value of x minus 2. You would also get just 3. 5 minus 2, 3, and then absolute value of 3, 3. Come to this side and choose a number less than or equal to 2. I'm going to go with negative 2. Negative 2 is less than 2. And plug it in here. Negative 2 minus 2, that would be negative 4. But then times a negative, that would be positive 4. So I plugged in a negative 2 and I got a positive 4. What happens if I take the same negative 2 and I plug it into the original? Well, negative 2 minus 2 would be negative 4, but when I take the absolute value, that would be just 4. So see how each of the pieces makes the absolute value work if you stick to the domain and choose numbers from the domain for each of those pieces. So let me now try this integral of the absolute value of 10 minus 2x. And so what I'm going to do is make it a piecewise function and then graph the piecewise function and then take the integral by looking at areas. Okay, so let me start by saying that the absolute value of 10 minus 2x is equal to a piecewise function. One will be the positive 10 minus 2x with some domain, and the other will be the negative 10 minus 2x with its own domain. And how do I know what the domain will be? I take 10 minus 2x and I set it equal to 0. So I get that 10 is equal to 2x, or x is equal to 5. And now 5 is my point of interest, so I make a number line, I plot 5, and I try numbers to the left and to the right. I'm going to try maybe 0 on the left, and I'll try 6 on the right. And I plug it into the argument. Don't do the absolute value, just do the inside of the absolute value. So if I try 0, I'll have 10 minus 2 times 0, and that would be 10 minus 0, or positive. And if I try 6, I'll get 10 minus 2 times 6. That'll be 10 minus 12, which is negative. And so what can you say about the top one here? Well, that was the positive 10 minus 2x. And we had a positive to the left of 5. So that means when x is less than 5. And what about the negative? Well, the negative came as a result of trying a number to the right of 5. So then the domain will be x greater than 5. And you have to set one of them to be equal to 5. So I'll choose the top one and leave it like this. Okay, so there's the first step. Change the absolute value into a piecewise function. Now I'm going to graph the absolute value, the piecewise function. Okay, so let's see. We are going to need an x and y axis. So there's my y. There's my x. And as you can see from above, 5 has to be a point of interest. So I'm going to let 5 be a point of interest. And so now I have to graph two pieces, 10 minus 2x and negative 10 minus 2x. So I can think of it as y equals 10 minus 2x and y equals negative quantity 10 minus 2x. Let me distribute that negative and I get negative 10 plus 2x. I'm just distributing here and I'm rewriting this equation. So basically I have two lines and I have to graph the two lines. Looking at the top one here, 10 minus 2x. How do I graph that? Well, the y-intercept is 10. I'm going to assume this is like 10 right there. And so the other thing to keep an eye on is this line, 10 minus 2x, shows up if x is less than 5. So when x is less than 5, I will have this line. And when x is greater than 5, then I'll have the second line, which is down here. Okay? So then to the left of 5, the y-intercept is 10. And what's my slope? Negative 2. You can say it's negative 2 over 1. So that means I will drop 2 and then run 1, drop 2, run 1, drop 2, run 1. And if I do that, if I go down 10 units, then it actually means that I went over 5 units. Because if I keep doing 2 over 1, 2 over 1, 2 over 1, that would eventually take me to 5. And that's the first piece of the function. And how do I graph negative 10 plus 2x? Well, negative 10 plus 2x, the y-intercept of that is negative 10, but it doesn't show up until after 5, and the slope is positive 2, so it'll be positive 2 over 1, positive 2 over 1, positive 2 over 1, positive 2 over 1, positive 2 over 1. And you can do some simple math and figure out that if you're going to be rising 2 each time, it's going to take you 5 times going up in increments of 2 to reach 0. So my line should start here and go that way. But again, keep in mind that this section of the graph only shows up for the domain of x greater than 5. So then I won't get to see this piece I'll just get to see it right after 5. So I should connect it right there. And that's how we create the famous V shape. It's actually two lines that intersect at the point of interest. So that's the graph that goes with the original integrand. Now I can think about the graph, think about area, and integrate from 0 to 6. So there's 0, 6 is somewhere here, and I'll be thinking about area. So remember, it's always the area between the curve and the x-axis. And so if I start at 0, from 0 to 5, I'm going to have this area. And then from 5 to 6, I'll have this other area. And both of these are above the x-axis. So I'll have a positive number added to another positive number. Okay? I'm going to call it area 1, area 2. And so now I know that this integral is going to be equal to the area of the two triangles. So we'll have 1/2 base 1 times height 1 plus 1/2 base 2, that's the base of the second triangle, times the height of the second triangle. And let's see, looking at the first triangle, we'll have 1/2. The base of the first triangle is 5. And what's the height of it? You have to go to the y-intercept to figure out that the height of the first triangle is 10. So 10 plus 1/2. The base of the second triangle, well, it goes from 5 to 6, so the base is 1. And what about the height? What would this number be? We don't know. We have to figure out what would it be if I hit the y-axis. Well, x is equal to 6, and so then you take the 6 and see if you need to plug it into the first equation or the second equation of the piecewise function. Remember that this line here was -10 plus 2x. So you plug in the 6 into that equation and you get -10 plus 12, and that gives you a 2. So the height of the second triangle is 2. I hope I didn't lose you there, but I'm just saying, if x is 6, what's the y if this is your function? So you plug in a 6 for x, and I know it has to be this function because that was the function when x is greater than 5. And it makes sense that it's less than 10. So 2 is a good number. And so now we can keep on going here. It's going to be 1/2 5 times 10, so that's half of 50, 25, plus half of 2, 1, for a grand total of 26. So just as a final statement, we can say that the integral from 0 to 6 of the absolute value of 10 minus 2x dx is equal to 26. And there was a lot of math that happened here. First of all, we broke down the absolute value into a piecewise function. We had to think about the domain for each one of those pieces. Then we had to graph it. But once we had the graph, it was very easy to say, oh, you have two triangles, let's find the area of both of them. And very important, both of the triangles are above the x-axis, so the area was positive for, not the area, but the area was above the x, and that makes it a positive number here and a positive number on the second expression. So 25 plus 1, 26. And now that we have the picture for the absolute value of 10 minus 2x, now we can answer questions regarding its integral. So here's a new question. What about the integral from 3 to 5 of the same graph, 10 minus 2x, the absolute value of it? How about I give you a few seconds? Or actually, I'm just going to give you the answer, so pause the video and try to work it out on your own, because the answer is coming up. Okay, so did you work this out? Here's my answer to it. If I want the integral from 3 to 5, then I'm only looking at it from 3 to 5, and that'll be this area here. So what I want to know is, I know it looks like a triangle. I would like to know, well, what's the height of that triangle? The height of the triangle would be the y value when x is 3. And what function am I looking at? Well, it's the first function, which was to the left of 5. And that would be up here when x is less than 5. That's 10 minus 2x. So then 10 minus 2x. If I plug in a 3, it'll be 10 minus 6, and 10 minus 6 is 4. So now I know the height of the triangle is 4, and the base is, what is the base? 2. So then the area will be 1/2, 4 times 2, which is 4. Is that the answer you got? I hope so. So here's an example of an absolute value function where I don't have to think about the piecewise function. So instead of the piecewise function, what I'm going to do is remember what the absolute value is doing, which is if the function is negative, it turns it into a positive. Okay? So what I'm going to do is I'm going to look at the function without the absolute value. That would be y equals negative x squared plus 2x plus 8. And I'm going to graph this without the absolute value. To graph it, I have to recognize that it's a quadratic, and so I think it opens downward because the leading coefficient is negative. And I would like to know the zeros of the quadratic. So I'm going to set it equal to 0. And I'm going to divide everything by -1 to make x squared positive. We want the leading coefficient to be positive. Now I can use the quadratic formula, or I can factor out, or complete the square. Yes, I think I am going to factor this out. And I think it's x minus 4 and x plus 2. Is that right? -4 times 2 is -8, and -4 plus 2 is -2. And then the zero factor property, so x is equal to 4 and x is equal to -2. And these are the zeros. This is where the quadratic crosses the x-axis. And I know that it opens downward. And I think that's pretty much it. I can now attempt to graph it according to what I have up to this point. So I'm going to try an xy plane, and at -2 I have a 0, and at 4 I have a 0. And what's halfway between -4 and 2? That would be 1. That's 3 units to 4 and 3 units to -2. So that's where my vertex is going to be. It's always halfway between the zeros. And so maybe somewhere here, I don't know. I'm not going to label a y point there. I'm just going to say at 1. And it opens downward. So it hits that point, and it hits that point. Okay? This is the graph of -x squared plus 2x plus 8. And what I want to do now is use this graph to figure out what would the absolute value look like. Well, the absolute value is just going to turn anything that's negative into a positive. And by negative, we mean anything below the x-axis will turn into something that now lies above the x-axis. So then maybe something like this, like that, and like that. Okay? So now that red graph, that's the graph we are integrating. And we are integrating from -4 all the way to 6. So that's going to take us from -4 to 6. Okay? So now again, let's think of it in terms of area. And what are the areas that we are accumulating? So from -4, it's going to be that piece. And then -2 to 4, it's going to be that piece. And then 4 to 6, that other piece. And for this, I cannot think of geometric figures because I don't really have triangles or rectangles or semicircles. I just have the quadratic, and the quadratic is not something that has a geometric formula for its area. But now thinking about the picture can help me figure out what my answer is going to be for this integral. So what we're going to do, let me move this. I'm going to break the integral up into 3 pieces. And why the 3 pieces? Because I have 3 pieces here. Roman numeral 1, I guess Roman numeral 2 in between here, and Roman numeral 3. And so each one of those pieces requires its own integral. Okay? So I'm going to say, let me push this aside. I'm going to say that this original integral is equal to the integral from -4 to -2. And why did I break it up to -2? Because that's my first section, from -4 to -2. And what am I integrating at that point, or on that interval? I'm integrating the red function. And how did I get the red function? Well, it's the opposite of the blue function that was below the x-axis. Okay? So what does that mean? To get the red function, you can think of it 2 ways. You can say you took the absolute value of the blue function, or you can say you took the blue function and you multiplied by a negative. Because isn't that what happens? If you have a negative and you multiply by a negative, then it turns positive. So then I'm going to say that I'm integrating from -4 to -2, and the function that I'm integrating is the opposite, or the negative, of the original function, -x squared plus 2x plus 8 with respect to x. But then I'm going to say, after you do that section, you need another integral, so plus the integral, and now it's going to be region 2, from -2 to 4. And what am I integrating at that point, -2 to 4? Well, -2 to 4, nothing changed. The red function is the same as the blue one. So then I can say that from -2 to 4, I'm just integrating the original function, which is -x squared plus 2x plus 8 with respect to x. And then I have to say plus one other integral, and that's the last region from 4 to 6. And what am I integrating at that last stage from 4 to 6? Well, it's the red function, which is the opposite of the blue function. It's the reflection, the opposite. And so that would be, again, the negative, or the opposite of -x squared plus 2x plus 8 dx. And see, by doing this, by having a picture of what the function looks like, then instead of doing absolute value and instead of doing piecewise functions, in a way, by setting up the three different integrals, you are doing your own piecewise function. See how this is three pieces? Three pieces. But we don't have to worry about much of the algebra as we did on the other, on the first example. Okay? So please take a look at the integrals and make sure you understand how we went from the graph to three separate integrals. Pay attention to the limits: -4 to -2, -2 to 4, 4 to 6. And very important, please understand why we have this negative here and that negative there. Because when you take something below the x-axis and you want to move it to the top or above it, you are taking the opposite of it. Okay? Now, if you integrate these three pieces, you will get exactly the same as if you were integrating the absolute value. Because again, by looking at the red function, that's exactly what we have. Having the two negatives here creates the effect of the absolute value. It takes a negative and it makes it positive. Now, in this video, I'm not going to integrate it and I'm not going to evaluate the limits because it's just tedious and the function is simple enough. I just want you to get the idea of how we use the graphs to take integrals of absolute values, and that in this instance we did not have to go to a piecewise function. We decided, hey, let's just graph it because we know how to graph the inside of the absolute value. So graph the inside of the absolute value, and then if you see any pieces below the x-axis, then make sure you go reflect them across the x, and that means make them negative when you take the integral. Okay, so I'll see you Friday in class, and then we'll have spring break, and I'll give you more details on Friday as to what we can do for spring break to make sure we don't forget some of the things we've learned lately. Goodbye.